All right, so we're going to start Ka and Kb, which what do you think that means? Starts with an E. Equilibrium of acids and bases, right? So if you haven't noticed, equilibrium is incredibly important for AP Chem. You have to do it for all sorts of different topics. So we're going to do Ka and Kb, same thing though, always products over reactants. We don't include liquids and we don't include solids. But in this case, we'll definitely have some sort of equilibrium. If it's a really strong acid or a really strong base, we assume complete dissociation, and so we technically have a really, really, really large Ka or a really, really, really large Kb, right? And then we're going to look at the pH of weak acids and bases. So that's kind of tricky, because right now, how do you solve pH? You do directly this, right? And then you say, all right, well, whatever she gives me as the concentration of H plus is going to be the pH, right? Except now we know if we have a weak acid, it doesn't completely dissociate, right? So we have some of it remaining as the acid with the H attached to it, and then some of it dissociates to H plus, right? We'll have to figure out how much dissociates into H plus. Because remember, pH is always how much H plus concentration is floating around. And then polyprotic acids we probably won't get to today. That just means that they can give off more than one H plus. All right, so the first thing is our acid dissociation constant Ka, and it's always equilibrium system. Now they can give you, I think last year they gave an equilibrium question, and they made it seem like you needed to do an actual equilibrium expression and calculate and solve, but really if you look at your Kas and the numbers are really, really large, then that's telling you that you have 100% dissociation, right? So pay attention to what your values actually are. But if we're solving for Ka, we're going to do the same way as before. Products over reactants. We don't include liquids. We don't include solids. If there's coefficients, what do you do with them? You raise it to the power. You make it the exponent, right? So for this one, this is our acid dissociation constant. Strong acids have a Ka value too, so even though we have a strong acid, you know this is one of your big six, it has a one-way arrow. Remember that you can write it with H2O, but you could also just write it as HCl, one-way arrow, H plus Cl minus. It's still going to be the exact same Ka setup, but it would just look like this. So this is just sort of the shorthand way, but it's still going to have the same exact Ka. So you do end up with a Ka value because it still is products or reactants, but we would assume that there's almost nothing left of this. So it's completely product favored, and so you would have a really large number of your species in that solution. So I just want to point out when you're finding, this is really important, when you're finding a Ka, you have to start with an acid. I know that seems ridiculous for me to even say, right? But you're going to get to a point where I'm going to give you base reactions instead of acid reactions, but I only give you a Ka value. So I can relate Kas and Kbs together, and I'm going to show you how to do that in a second, but recognize that the reverse of this reaction is a base picking up an H plus and coming to an acid, right? And then the the HCl is going forward, this is the acid. If I started this and I wrote this in the reverse direction, then this would be starting with a B, right, a base. So I just want to point out that if you're going to use Ka values, then write an acid reaction. You can't start with a base and use a Ka value. These are all the little things that I'm saying should be on like a notes page somewhere because you're going to have to pay attention to these details. All right, so here are some acid dissociation constants. Obviously, HCl is a really strong acid. It has a really large Ka value. Nitric acid, large Ka value, but not nearly as large as HCl. 30, and then we get to some of these which are smaller, so these are our weak acids, right? So again, I'll touch on this eventually, but this can behave both as an acid or a base because it can pick up an H plus or lose another one. So this has a low Ka value. lower, lower, lower. So the lowest Ka values are going to be the ones that are the weakest acids. So down here, hydrocyanic acid is the weakest of the acids. So you're just going to look at acid dissociation constants to tell you which acids are the strongest. You have to just make sure you remember to do that. So the larger the Ka, the stronger the acid. All right, so a base dissociation constant. So this is what I was saying before. You can use Ka values, but then you write an acid reaction. If I'm going to use a Kb value, then I need to start with a base reaction, right? So use Kb values, then write a base reaction. That means that you have to start with the base. So bases are always going to pick up an H+, right? Acids are always going to give off the H+. So if you're starting with the base reaction, you write NH3. Again, you don't necessarily have to add the water there, but without the water, it's kind of hard to see where you would pick up the H from. So a lot of students just include water all the time because it just makes it easier for them. So NH3 picks up the H+ to make NH4+, and then OH-. And so it should be products over reactants, and you're starting with the base reaction, so then it will be your acid over your base. All right, so same thing with your Kb values here. So a very, very large Kb value indicates that you have mostly products, right? And then that means that it's a really strong base. Ammonia, NH3, is not a very strong base. ClO-, do you remember that one? What's the name of that polyatomic ion? What? Hypochlorite, right? Because chlorate is ClO3-, ClO2- is chlorite, ClO- is hypochlorite. And then you should pay attention, right? Anytime that we have these nitrogen-containing compounds, even though you're not familiar with them, what should you recognize? Nitrogen has what on it? If you were to draw the structure, it has a lone pair. So if you're not sure, then I guess you could draw the structure, but just pay attention. Anytime you see a nitrogen-containing compound, likely has a lone pair. If I'm going to turn it into the acid, then I'm going to add the H on it, and I'm going to put a plus sign. That's what you do. It picks up an H. So you would just add the H. Like here, I probably would write it here, H3NOH, and then put a plus sign on it. So when you're adding H's, they get their plus sign. In this case, it wouldn't because it's already a negative. You would add an H+, and it would just cancel that negative. Same thing here. You add the H+, it becomes positive, so NH4+. So the stronger the base, the larger the Kb. All right, pKa and pKb values are often given. So they'll give you a question, and instead of giving you the Ka or the Kb because you need it, they'll give you the pKa or the pKb. But P of anything means what? Negative log. You can find the P of anything. I can find the P of Mrs. De Bruin, the negative log of Mrs. De Bruin. Whatever it is, just P means negative log. So if I want to find pKa, it's the negative log of the Ka, so the same thing that you did yesterday, if you want to find the Ka value, you're going to take 10 to the negative pKa to solve for the Ka. You need the Ka because you can't figure out the equilibrium, any of the concentrations of the ions, without the Ka value. So you're going to have to find the pKa and the Ka and how they're associated. Same thing with pKb and the Kb. All right, so what I wrote up here for you before is that we can solve for the Ka and Kb by using Kw. It's just basically saying these acids and bases dissociate to give us the K of water at 25 degrees. And then another thing that you should know is that the pKa plus the pKb is equal to 14. So you can kind of go back and forth with those numbers as well. And again, you'll end up choosing which way you want to go for these to solve for them. It's sort of like how you could choose here and here, which way you want to go. But they all those equations work. All right, so find Ka at 25 degrees C for hydrocyanic acid with a pKa of 9.31. So if you're given the pKa, you can just set this up. Ka is equal to 10 to the negative pKa, and then you plug in your pKa value, which is negative 9.31. All right, so reverse of what you did, same thing with pH. If you have your pH, you take the decimals, and the decimals become the sig figs. If you have a pKa, you take the decimals, and the decimals become the number of sig figs. So because this has 2 decimals, then it needs to have 2 significant figures in the Ka value. Same thing with pH, right? pH has 2 decimals, then the H plus concentration would have 2 sig figs. So make sure that you pay attention to that. So this is our Ka value. It's really low, which means that HCN is a weak acid. Got it? Right? That's how we can pay attention to the Ka values. All right, so if you take a look at all of the pKa values here, what do you notice about the smaller the pKa? The stronger the acid, right? So you have to sort of associate that. We already said if it has a really large Ka value, large Ka values are going to mean that it's a really strong acid. But if you take the negative log of that, you're going to get a small number. So the smallest numbers are going to be your strongest acids. Think of it the same way with pH. The pH scale makes a lot of sense, right? You know really low numbers are very acidic. Well, for something to be very acidic, it has to have really a lot of H plus in it. And that would have a very strong acid. So if you're taking negative log of H plus, a lot of H plus would give you a very low pH. If you take a Ka and you take the negative log, a very big Ka will have a very low pKa. All right, so same thing as before, you're just looking at different Ka values to determine the strength of the acid, and then the smaller the pKa, the stronger the acid. Everybody good so far? That kind of stuff, I mean, maybe just memorize that, but you understand K is products over reactants. So if it's a big number, it has to mean it's product favored, which means it's a strong acid. All right, same thing with pKb. Sodium hydroxide has a very large number, gives you a negative number. Then ammonia, a weak base, and then going down the list, we have weaker bases, and then the pKb value goes up, the weaker the base. All right, so your relationship between Ka and Kb. So here's the basic reaction. So this is what I was talking about up here, right? If you have a Kb, then you need to write your reaction with a base. So this is a base. Kb reacts, well, goes in water, pulls off the H plus from the water to make ammonium, the acid, and then the conjugate base, right? So this is base, acid, conjugate base. I write my Kb value to be my products over my reactants. If I were to write the opposite of this reaction, I would write NH4 plus goes into water. Not plus OH, but NH4 plus goes into water. This is the acid. So the acid then is going to donate its H to the water. This becomes the conjugate base, and then this is your conjugate acid. If I were to write the Ka reaction, it's NH3 times H3O plus over NH4 plus. So these values are the reverse of each other, right? The reversed reaction. So you have to be super careful that if I give you a Kb, that you don't write a Ka reaction. And you're going to see that on a bunch of problems, because I could give you, say, this reaction, but just give you a Kb value just to mess with you, because that's what the AP exam would do, right? That just means don't use the Kb value here. You need to use Ka, and that's where you're going to go and use this equation to solve. So the next slide, I'm going to show you how they come up with that. So this is the first one is your what? Ka or your Kb setup? How to be your Kb, this first one, right? Because this is your reactant, products over your reactants. So this was your Kb, this is your Ka. So look what cancels, right? And it's just the concentration of OH times the concentration of H plus gives you Kw, which is what we did yesterday, right? So then if I want to know what my Ka and my Kb, it's going to be the same exact thing. It's equal to 1 times 10 to the negative 14th. So this is just showing you a whole bunch of equations mixed in here, but it's essentially what I just wrote. Kw equals Ka times Kb. If we take the log of each of these, then the pKw is equal to the pKa plus the pKb, which pKw is 14, because negative log of 1 times 10 to the negative 14 is 14. So pKa plus pKb equals 14 at 25 degrees. Or we can say this concentration, same thing as before, pH plus pOH equals 14. I gave you that yesterday. So all of these are really helpful. Some of them are on your equation sheet, some are not. You okay with that? All right, calculating pH for strong base solutions. Pretty simple, we did this yesterday. Find the pH of a 3.5 molar sodium hydroxide solution. I added this sort of in earlier today, we already saw this. So since it's a strong base, we assume complete dissociation. If you wanted to find the pH of it, you have to recognize that you're actually finding pOH first, right? Or you can do what? If you're given the 3.5 molar sodium hydroxide, what's the other approach? You just did this. Well, I'm saying you could use this. Where did I put it? You could use this to find the pH, right? But you first have to find, or you could use this and then this, right? There's two different approaches. So this, or you could take your this and find your pOH that way. So whatever approach you want to do. All right, so since it's a strong base, we can assume complete dissociation. So it goes from 3.5 molar sodium hydroxide is actually 3.5 molar sodium and 3.5 molar hydroxide, right? I always suggest that you write out your reactions because some of you, like today on the Quizlet, you just missed that this was going to be doubled when I gave you that calcium hydroxide. So if this is 3.5, then this is 3.5, then this is 3.5. So in this example, we just took the pOH is negative log of 3.5. You get the pOH, and then 14 minus that is going to give you the pH, which is 14.54. So sort of to what Mike was saying earlier, you can extend beyond the pH scale for something that's very strong, either acid or base. Yes? All right, so now we're going to look at our pKa and our pKb values. An acid was dissolved in water, and the pKb value associated with its conjugate base was found to be 15.5. Right, so notice that this is sort of tricked already. What did you dissolve in water? An acid, but it's giving you a pKb value, right? And a pKb value just tells you about its base, not about its acid. So the conjugate base has a pKb of 15.5. What did we learn already about that? So low pKbs are strong bases. So since this is a high pKb, its conjugate base must be a weak base, which means that the acid must be strong. Get it? Did you follow that all? So I always say be smart before you start because you should think about that stuff. That should sort of make sense to you before you're starting a problem. All right, so what's the pKa value for this acid? What are you going to do? Easy approach, right? That's why I say you have all these things here. Yeah, so you're just going to subtract, right? Go ahead. So because we said we should have a very strong acid, what should the pKa be? Really low, right? And it is. We get negative 1.5. Correct? Because 14 minus 15.5 gives you a negative 1.5. So this must be a very strong acid. I keep repeating this, but is the solution acidic or basic? Clearly acidic, right? Because, well, our pKa tells us that it's a strong acid, but it already said an acid was dissolved in water, right? Is the conjugate base a stronger or weaker base than water? So what's the thought process there? So first of all, what is this, a one-way arrow or a two-way arrow? A one-way arrow. So whatever our acid is, it goes into water, and this is our acid, and this is our base, and then we get a conjugate acid, which is going to be the H3O+. So this is your conjugate acid. And then you're going to get some base. So I'm going to call that, A-. right? Because this would have been HA, whatever this is. So this is my conjugate base. So is the conjugate base a stronger or weaker base than water? Conjugate base has to be weaker, right? If it were strong, then it would be competing for the H+, and it would rip it off of it and drive it back to the left to recreate that acid, wouldn't it? And then if that's true, then that would be a double way arrow, and we would have a weak acid. But because this is a strong acid system, it completely dissociates the H+, and then water and A- are competing, but A-, since this is a strong acid, this has to be a weak base, right? We've already clarified that, but you can think of it in so many different ways too, about competing and one-way arrow and a strong acid and all that. Make sense? Okay. Find the pH of a 2.5 molar solution of HF. All right, so this is, we've just switched. Your mentality has to now recognize if this is a big 6 acid or not. So if you don't know your big 6s, it's impossible for you to move forward, right? Because all you would do now, if you assumed this was a big 6, is you would just find pH directly like we've been doing. Can you do that? No, because HF is a weak acid and it doesn't completely dissociate. And remember, pH is a measure of how much H+ is in the solution, right? We don't know how much H+ is in solution because we didn't assume complete dissociation. So now you have to use equilibrium to solve. So this is a weak acid, it turns into the acid in the base, and it gave me a pKa value. So if I want to find pH, what do I need? Here's your equation. What do you need? Concentration of what? Every time they ask you for pH, you need to somehow find H+ concentration. Somehow. It's going to be a whole variety of ways to do that, right? You might be given a base reaction, and you find OH concentration, and then you have to kind of do this thing and find pH again. But you're always looking for H+ concentration for pH. So if I have here a weak acid, they gave me my pKa value, right? Essentially, what I'm looking to do eventually is come up with H+, and this could be H3O+ or H+, times F- is over the concentration of HF. That's eventually where I'm trying to go, because then I can solve for this piece, right? And remember with equilibrium, when we did this, we came up with ice charts and all, we did all that. We'll do that again. But that should sort of be familiar to you of how you solve for this. This becomes x squared over 2.5 equals some Ka value, and then we solve for x. Same procedure every time. All right, so first we need a Ka because we can't plug in pKa. So how do you find Ka from pKa? 10 to the negative pKa, right? So since the pKa has 2 decimal places, how many sig figs should I have? 2. So plug that into your calculator, right? We cannot leave that as the expression. You can't write 10 to the negative 3.14. You actually solve for it. So when you're done, check that you got the answer. So we got 7.2 times 10 to the negative 4th, right? So that right there is kind of also indicating that you have a weak acid because you have a low Ka value. All right, so now we're going to solve for H+ by plugging in essentially this expression here. So let's just kind of relive rice charts. It's going to be, right, your whole reaction is here. I'm going to put the arrow in so you see it. We dropped water because water is not part of it. So if we're calling this a rice chart, that's what it is. Our initial concentration of HF is what? 2.5, right? What's H+ and F-? 0. So how much does HF go away? Minus x, and H+ and F- increase by plus x. And then we solve for our equilibrium, which is x times x over 2.5 minus x. You remember this whole thing about quadratic equations and how we'll never have to use them? So what do we assume that little minus x is? It's what? Negligible. Meaning that this is such a weak dissociation that we're not really concerned about how much of it is going to convert or go away. So we're just going to eliminate it. So what is the rule about eliminating?
Larger than 10 to the
Yeah. And it will be, right? It's always going to be. But you can solve for x and then go put it back into your expression and make sure that it didn't change your Ka value. That's really the easiest technique rather than trying to memorize numbers. All right, so now we're going to put this into our Ka expression. So H plus, F minus, HF. We get rid of our little x because we assumed that it was negligible. And then we're going to solve for x squared. Okay? Make sure you can do this in your calculator. All right, so you solved for H plus, but the question is specifically asking you to find pH, right? So now you're just going to plug that into your negative log of the H plus concentration. And then because your concentration had 2 sig figs, then your pH should have 2 decimals, 1.38. So I just want to point out here, we do have, perhaps you would assume, a low pH. But when we were looking at, say, like hydrochloric acid, the pH was negative. It can be. And I want to just point out that the molarity of an acid doesn't indicate the pH. So I could have a 2.5 molar hydrofluoric acid, and I could have a 2.5 molar HCl. What determines the strength of an acid is how much H plus is floating around, right? So if HF doesn't dissociate very much into H plus, it doesn't matter that it was 2.5 molar. It just matters how much of it is actually going to go into the H plus, okay? Moving along. Find the pH of a 1.5 molar HCN solution given your pKa here. So similar approach, you're going to solve on your own this time. I'm not going to guide you through that. I bet you can get through it to the end. Okay, so let's just flip through. Ka was 4.9 times 10 to the negative 10th. 2 decimal places gives you 2 sig figs. Ice chart should read this. You plug it all in. pH is 4.57. You got the correct decimals? Okay. I guess we'll stop there. So we'll look at some homework over the weekend. Okay. So the only other way that a question is going to be given to you on an AP exam about equilibriums for acids and bases is they tell you how much actually gets dissociated. So instead of giving you your Ka value here, they're going to ask you to solve for it by using something called percent dissociation or percent ionization. So remember the 2 words. Dissociation means things are breaking apart. Ionization means that something is being ionized, which also means something's breaking apart. So in any of these reactions, this dissociated and then this piece ionized. They can use either word. It just means that something is giving up an H+, something's accepting an H+, and here's the amount that it's going to do it. It's going to do it by, like in this question, 0.767%. So when they give you the percent, that's your change. That's the amount that's going to be going away. So if I started with a certain concentration of this, 0.3 molar, 0.767% is going away. It's turning into products. That's what this means when it says percent ionization or dissociation, sometimes they might use. So if this part goes away, I can just subtract out that much. That means that my products are going to increase by that much. It's really the same problem, just understanding the vocab. So what do we start with for this? 0.3 molar. What are our initial concentrations on the other side? 0 and 0. I just want to point out that sometimes your products could have an amount to start with. And if they do, you set up your ice chart the same way, and you would just add to it by the time you got to your equilibrium. So if they tell you that there's already some acid in the beaker, you're just going to start with it in your H plus in your initial line. All right, so now my change is going to be minus x plus x plus x, but we know what the change is, right? So here's going to be the minus x plus x plus x, and then equilibrium shows us that, but we can find x and just plug it in. So 0.3 molar multiplied by my percentage as a decimal, so don't forget to move your decimal place 2 to the left. This will give me the amount that goes away, which means that that amount gets added to both of your products. Okay, so if this is our x value, now we're going to plug it in, and you're literally going to subtract that out of that 0.3, right? We're not going to eliminate the x in the equilibrium line. We're going to put it in there. So when we solve for it, these are both 2.30 times 10 to the negative third squared. But normally we eliminate this x. We're not eliminating it because it's telling me the value that it is, and it's not negligible. It actually is something that should be subtracted out. So now I subtract that out, I solve for it, and I get my Ka value. So now that we know our Ka, we can find our pH. How do you find pH always? Concentration of H plus. So technically, I didn't really even need my Ka value there to solve for it. I could solve for the pH just directly from the ionization. So if I know my H plus concentration, which we do, we're just going to solve for it by using the negative log of that. So you just throw that in directly. Make sure you pay attention to your number of significant figures in your concentration is how many. So then your decimals in your pH need to be 3. I will be giving points for that tomorrow on your quiz. In any spot. You don't know when I'll give you the point, but it'll be definitely in there. So here's, we can easily do this problem because we did this earlier, and we also, it's the exact same thing as calculating the Ka and the pH and all that for a weak acid, except we're going to flip it to a weak base. So tomorrow on your quiz, this is the one area where students get a little tripped up because you forget to recognize that this is a base. Do you see how it doesn't say? The question will just read that. It'll say find the pH of this solution. So if you don't recognize this is a base, you're going to start trying to write acid reactions, and that's not going to happen for you. So this is really important that you recognize how to write that. And it's really important that you recognize if it's a one-way arrow or a two-way arrow because you're going to find pH 2 different ways, right? pH for a strong is direct. Same thing for a strong base, you would find pH, POH directly. If it's weak, then you have to do KB or Ka. All right, so this is a base. It's a weak base, so I'm going to have to solve for KB. So what is your first step? To write your reaction. I'm not writing it for you tomorrow. So your first step would be to write your reaction, right? So if you write out your reaction, now you can solve for this problem given the KB or the pKb. You solve for your KB by doing 10 to the negative, right? So 10 to the negative 4.74 gives you your KB value. Same thing that we did for Ka, right? One of your clues might be that I gave you a KB value, and then you would say, oh, well, she must be giving me a base. That's a possible clue. But what could I do, or the AP exam? I could give you a Ka and still ask you to do it for a base. What do you do if I give you a Ka and you recognize, hey, this is a base? Not that one. That would be if I gave you a pKa. If I gave you a pKa, then you could do 14 minus the pKa to come up with the pKb. I would do Kw. Right, Kw is equal to Ka times Kb. Okay? So just recognize, I don't remember if I do that on your quiz tomorrow, but the AP exam is notorious for giving you weird little setups like that and making sure you know what you need to do. All right, so we solved for Kb. Now we're going to do what? Kb equals? Any K equals? Products over reactants. And since you already have the reaction, you write that out. And you're going to write your ice chart. We don't know what our final products are, but we do know it's a weak base, so then the denominator is going to be the 3.5, right? And then we have our x squared values. I mean, you don't have to write an ice chart every single time, but they might help you. So the question originally wants to know what the pH is, right? But we're going to have OH concentration. So two approaches. What you can find POH by doing negative log of this, and then what? Subtract from 14, or if I have OH concentration, Kw is equal to H plus times OH concentration, and then you could solve from pH there. I think 14 minus the POH is faster, but it's up to you. So now we know OH, we can solve, and then subtract from 14. Make sure you use your decimal places to match your sig figs and your concentration. And then a good check is to recognize that your pH should be in the basic region. If you have a pH below 7, you probably messed up somewhere. And since this isn't a strong base, your pH should not be close to 14. It should be in this range, right? Something between a 13 and a 14 is going to be a strong base. Something that's a strong acid is going to be between like a 0 and a 1.5 maybe. And then weaks are going to fall in sort of any range. All right. So this is the same exact approach that we did with the acids, but now we're just doing it with the bases. So here's another problem. A 0.15 molar ammonia solution has a pH of 8.75. Find the Kb. All right, so think about this in your head. If you're finding Kb, you're going to do products over reactants. I know this concentration, but I don't know these directly. How am I going to find them? What information in the problem is giving me to find these two? We're not solving for x squared this time, because if I was solving for x squared, it would have been giving me the Kb, but I'm finding Kb. So I need to know both my numerator and my denominator. So what piece of information? It gives you what? It gives me not OH, it gives me pH. All right, so if I have pH, I can find essentially this OH concentration. So I can subtract this and do POH. 10 to the negative POH would give me this. What about this? Think about all your ice charts that you've been making. This would have been 0.15 minus x, 0.15 minus x. This would have been 0, 0, plus x, x, x. So if you know what x is, then this is going to be x, right? So think about how you would set up your ice chart. You're essentially just going to find OH concentration from here, which will be the same as this. Because it's a weak base, the concentration of this is not going to change much because it's negligible, the amount that does change. And then just solve numerator divided by denominator to find it. So step 1, find your POH. So 14 minus 8.75 gives me 5.25. So now we're going to find OH concentration, which is going to be the same as the NH4 because it's X in our ice chart. So 10 to the negative 5.25 gives me 5.6 times 10 to the negative 6. Recognize that you had to go backwards this time. So given the POH as 2 decimals, then my sig figs and my concentration can only be 2 sig figs. It's going backwards. So 5.6 times 10 to the negative 6 molar. Okay, so after we find our concentrations, like I said before, we know that the ammonia doesn't change by much. So we can just ignore the change and plug in the concentration directly. So you just plug in all of your values for your numerator and denominator. You solve for Kb. If it asked you to find Ka, you would just do Kw is equal to Ka times Kb. Remember, Ks don't have any units, so this answer is acceptable. Okay, moving along. So this is just a little bit of theory, really fast. Anything that can donate more than 1 H plus is called a polyprotic acid. So polyprotic acid can be an H2, an H3, probably not an H4, but usually it's an H2 or H3. Like, for example, carbonic acid is H2CO3. That can donate 2 H pluses. Sulfuric acid can donate 2 H pluses. Phosphoric acid, that's H3PO4, can donate 3 H pluses. So every H plus that can be donated has its own K value because K tells you how much H plus is going to be ionized or dissociated. So for these examples here, both of those H's are going to go away, but we always assume that the first K value is going to be the strongest dissociation, or the one that dissociates most of the H plus. So take, for example, carbonic acid. This first dissociation goes to this, and I just want to point out that sometimes the AP exam will tell you they're giving you a polyprotic acid, but they don't actually give it to you. They will just do something like this, H2A, right? It'll say the following polyprotic acid has a Ka value of blah, blah, and they just put an A. So it doesn't really matter what it is. You just have to recognize that you're looking at the Ka values. So this first dissociation gives you off this first hydrogen. So you don't remove both of them, you just remove one of them. And it's a double-way arrow here because carbonic acid is not as strong. Now if this were sulfuric acid, we would still one-way arrow it and take off both H pluses, okay? So H plus, and then this is the second acid, so you're gonna write it as a second dissociation. So you only remove one acid at a time, hence the 1 next to the Ka1. So this dissociation is stronger than this one. This is my second dissociation in which it takes off the second H plus. So when we do our calculations, even if it's for a weak acid that has 2 hydrogens, we always take the value to do all of our calculations from the first acid. They may give you 2 of them, but you're going to do it for this first one, okay? And I just want to point out, when we did equilibrium, a long time ago, we could come up sometimes with like a final reaction, not given these 2, but say we wanted to come up with a final one. If you're coming up with a final K value, you multiply Ka1 times Ka2. Kind of like a Hess's law where you cancel things out and you come up with a final equation. It's not for this one, but if it did, just so you remember, to come up with new K values, you multiply them. So Ka times Ka1. And this is what I just said before. Always use Ka1 to calculate H plus and pH. Most of the H plus ions come from the first dissociation. The H plus ions from the first dissociation drive the equilibrium for the other dissociations to the left. So let me just show you what that means for this. If I have first, this H plus comes off, what it's saying is that you have a common ion here. And remember, common ion effect, according to Le Chatelier's, if this is the second reaction, is going to shift this one left. So the idea is the amount of H plus that's coming off from the second reaction is so insignificant that we're sort of just going to ignore it because it drives it even further to the left. And that's a really, really small value. So that's what it means by it's going to shift the second reaction to the left due to common ion. All right, so that's it. So we're going to practice some of your problems now.